Okay, we're going to talk about image formation and radiographic quality. This is your FOBR in Chapter 3, and it's a good chapter to help explain some of the concepts we talked about in the other PowerPoints. So here's your objectives. Like I said, as always, make sure you are able to define the objectives. So, image formation. When we talk about image formation, we're going to talk about differential absorption. So differential absorption is anatomical tissues absorb and transmit X-rays differently based on their composition. So we talked about the different compositions based on atomic number with the air, water, muscle, and fat, bone. All of them have different atomic numbers, which is going to give us differential absorption. So bone absorbs more X-rays than muscle. So attenuation is the primary beam loses some of its energy, so a number of the photons as it interacts with anatomical tissue. So when it does that, if there's any kind of attenuation, what we're looking at is absorption and we're looking at scatter. So as the primary X-ray beam interacts with the anatomical part, photons are absorbed, they're scattered, or they're transmitted. So it's the three things that can happen. They can be absorbed, scattered, or transmitted. So the difference in the absorption characteristics of the anatomical part creates an image that is structurally represents the part. So as you can see here, the primary photon comes in and it can be absorbed where it's just, you can see here in the bone, where it's just stopped. So the bone has absorbed that photon. It can be scattered, so you can see here it's coming off to the side. So scattered radiation is any photon that changes direction is considered a scattered photon. Or it can pass through and hit the image receptor, so transmitted. So during absorption, the energy of the primary beam is deposited within the atoms comprising the tissues. So photoelectric effect is what we're talking about here. Photoelectric effect is complete absorption of the incoming photon. So the X-ray ionizes the atom, the lower energy secondary X-ray photon is created, and the probability of photoelectric effect depends on the energy of the incoming X-ray photon and the tissue atomic number. So scattering. When we talk about scattering, we're talking about Compton effect. So Compton effect occurs when an incoming photon loses some, but not all of its energy, then changes its direction. It can occur within all diagnostic energies and is dependent only on the energy of the incoming photon, not the atomic number of the tissue. So that's the difference. Higher kVp reduces the number of interactions overall, but the number of Compton interactions increases comparison to the number of photoelectric interactions. So the higher the kVp, the more likely you're going to have a Compton interaction. So looking here, absorption versus scattering. So if we look at the photoelectric effect, you have the incoming photon interacts with the inner shell, so K or L shell, and it gives all of its energy and ejects out an electron. So here, so it's absorbed and it ionizes the atom and it ejects out an electron we call a photoelectron. So then there's a vacancy in the K or L shell, and then the electron from the outer shell drops down into the lower shell, giving us a cascade effect. So we have a characteristic cascade. All right, with Compton effect, this is scattering. Compton scatters, another way to remember it. The photon interacts with the outer orbiting electron, imparting some of its energy to the electron, ejecting it from orbit. The ejected electron here, so number 2 right here, is the Compton electron, leaves the atom an energy equal to the excess imparted by the photon. So then there's a photon continues in an altered path, scattered less energy in a longer wavelength. So here it deposits some energy here and the original photon loses energy here. So when we're comparing the two with photoelectric effect, the incoming photon has sufficient energy to eject an inner shell electron and may be completely absorbed. An electron from an upper level shell fills the electron hole or vacancy. A secondary photon is created because of the difference in the electron binding energies. The probability of this effect depends on the energy of the incoming photon and the composition of the anatomical tissue. Fewer photon interactions occur at higher kVp, but of those interactions, a small percentage are photoelectric interactions. So with Compton, an incoming photon loses energy when it ejects an outer shell electron and changes direction. The scattered photon may be absorbed within the patient tissues, leaving the anatomical part intact with the image receptor or expose anybody near the patient. So this is what we call the dose that we get. So Compton is the dose that is the occupational dose. The scattered photon will strike the image receptor, providing no useful information. So any scattered photon from Compton effect does not give us any useful information. The probability of this effect depends on the energy of the incoming photon, but not on the composition of the anatomical tissue. So fewer photon interactions occur at higher kVp, but a greater percentage of those interactions are Compton interactions. So factors affecting beam attenuation. So tissue thickness, we've got tissue type, tissue density, and X-ray beam quality. So the thickness, X-rays are attenuated exponentially and greatly reduced by 50% for each 4 to 5 centimeters, so 1.6 to 2 inches of tissue thickness. So with the tissue type, tissues composed of higher atomic number will increase beam attenuation, and tissue density, increase in the compactness of the anatomical particles, will increase the beam attenuation. So with the X-ray beam quality, the higher the kVp increases the energy of the X-ray beam and will decrease the beam attenuation. So it's more likely to pass through. So here you can see this is a thinner patient transmit more radiation than a thicker patient, and a thicker patient absorbs more radiation than a thinner patient. So I'm looking at these two and I find this interesting. So this patient has is showing this patient is thicker, so I'm kind of confused as to what they're showing here. So in theory, the thicker the patient, the more X-ray photon absorption there is. So tissue type. This is big because this is going to go into our contrast scales. So bone absorbs more radiation than fat and air transmits more radiation than fat and bone. So you can see bone is most dense, so it's going to absorb more of your photons. Then fat, and then air. You can see air has the most passing through. Beam quality. So the energy of the X-ray beam affects the interactions within the anatomical tissues. So lower kVp results in more absorption in the tissue, and higher kVp results in more transmission through the tissue. So you can see here with the low energy kVp beam, you can see it's absorbed by the tissues, where a higher energy beam is more likely to pass through. Okay, so this is what we call an up and down chart, and this is found in Faber. We're going to be talking a lot about this. It'll be in your physics books, also for Carleton. So we're going to go through the whole body with a bunch of different factors, and you're going to be able to tell me what's going on. So here with tissue thickness, if we increase the thickness of the body part, we're going to increase beam attenuation, increase absorption, and decrease the transmission of photons. So, and then it's reversed here. If you decrease the thickness, you decrease the absorption, the beam attenuation, absorption, and you increase the transmission. So with the tissue atomic number, so increasing the atomic number increases beam attenuation, increases the absorption, and decreases your transmission. And you decrease the atomic number, you decrease the attenuation, decrease absorption, and increase the transmission. So same goes for tissue density. So if you increase the tissue density, you increase beam attenuation, increase absorption, and decrease transmission. and decrease in tissue density decreases your beam attenuation, decreases absorption, and increases transmission. Then your X-ray beam quality, and that is your energy of the beam, which is your what? KVP, yes. So increasing beam quality decreases your beam attenuation, so it passes through because it's higher energy. It decreases absorption because it's higher energy, and increases your transmission, where if you decrease your beam quality, so decrease your KVP, you're increasing your beam attenuation, you're increasing your absorption, and you're decreasing your transmission. So that's what this up and down chart represents when we're talking about the subject and how it affects the image. So exit radiation, when we talk about exit radiation, we're talking about the remnant beam. So it is composed of transmitted and scattered radiation. So the varying amounts of transmitted and absorbed radiation creates the image that structurally represents the anatomical area or interest. So scattered radiation reaching the image receptor is considered unwanted, and we call that fog. So we only want photons that are coming straight through the patient and are absorbed to give us the difference in the densities of the anatomical parts. So the scattered radiation is unwanted density, and it degrades our image. So absorbed radiation creates increased brightness or whiteness on the displayed image. So transmitted radiation creates the black on or darker shades of gray on our image. So the various shades of gray recording in the image make up the anatomical tissue so that we can see the differences. So as you can see here, we can see the spine, so it's absorbed more X-ray photons, so it's brighter, whereas here we've got a gas bubble, and you can see that it passed right through, so we've got black. You can see the psoas muscle right here showing us muscle. So you can see the difference in the density between the bone and the muscle and the air. So big difference. So radiographic quality. An X-ray radiographic image accurately represents the anatomical area of interest, and its information is well visualized for diagnosis. So visibility of atomic structures, we're looking at brightness and contrast. We need those two to see anatomical structures. And accuracy of the structural lines, or our sharpness, is our spatial resolution and distortion. So if we're talking about radiographic quality and we're talking about visibility, we're talking about here brightness and contrast. So maybe this graph will help you remember the difference between the two. If we're talking about sharpness, we want to look at spatial resolution and distortion. So image brightness. A digital image is evaluated by the amount of brightness or luminance, so light emission, on the display monitor. So I'm going to talk about luminance when we talk about the display monitor. A film image is evaluated by the amount of density or overall blackness of processing. So on the display monitor is luminance. When we talk about film, we're talking about overall density on the image. So we need to have sufficient brightness to visualize anatomical structures of interest. So here you can see it looks like a pretty good knee to me. So image with excessive brightness. I can see trabecular lines. It looks pretty diagnostic to me, but it is a little bright. And then you can see here, this is without enough brightness. It's pretty dark, so we'd be able to window that. And in film days, we couldn't fix that. Image contrast. So the radiograph must exhibit differences in brightness levels or density, so image contrast, in order to differentiate among anatomical tissues. So the range of brightness levels is a result of tissue differential absorption of the photons. So as you can see here on this image, we have sufficient brightness but no differences. So there's no contrast in that image. It's just one density. Where here we have varying levels of brightness. So we have some contrast in the image. Subject contrast. It's the result of absorption, characteristics of the anatomical tissue radiographed, and the quality of the X-ray beam. So it has to do with your KVP and your tissues that you're X-raying. So the ability to distinguish among types of tissue is determined by the differences and brightness levels on the image or contrast. So contrast resolution describes the ability of the image receptor to distinguish between objects having similar and subject contrast. So we talk about grayscale and scale of contrast. So grayscale is the number of different shades of gray that can be stored and displayed in a digital image, and our scale of contrast is the range of densities visible on film. So if we're looking here, we talked a little bit about our scale of contrast. So we have high contrast here, and what it is we have bone, fat, and air. So we only have big swings between total absorption and very little photons passing through to photons completely passing through. So it's going to be real black and white. So very few shades of gray in between. Where we look here, we've got muscle, water, and fat, which are all pretty similar. So you're going to have just slight variations between the shades of gray here. So the chest is the area with the highest subject contrast because there's air and the mediastinum, which is bone and tissues within the mediastinum. So here is the scales of contrast, and we've talked about this already. So we have high contrast, which is also high contrast short scale. So there's few shades of gray. So this would be your low KVP. When we have low contrast, we have long scale, which is high KVP. So you probably remember this from the prior PowerPoint. Spatial resolution. So anatomic details must be accurately recorded with the greatest amount of sharpness. So spatial resolution refers to the smallest object that can be detected on a digital image. The radiographic images have some degree of unsharpness, and we talked about that before on how the edges, we have that penumbra, I like that. All right, distortion. Radiographic misrepresentation of either size or shape of the anatomical part. So size distortion or magnification is the increase in the object's image size compared to its true or actual size. So we're talking about SID and OID, and those are the two that affect magnification. So you want the longest SID and the shortest OID to decrease your magnification. Shape distortion is a misrepresentation of the object's image shape. So you have elongation and foreshortening. So that has to do with the central ray alignment and the X-ray tube. It also can be the part position and the image receptor. So if you have an angle on any of those, you're going to have distortion of the true size and shape of the body part you're imaging. So you can see here on the chest x-ray the person is breathing, so you can see motion and sharpness. And this is shape distortion, so you can see here with either the angle of the tube or the angle of the image receptor, we have foreshortening, and here we have elongation. So this is longer than it should be, this is shorter than it should be. This looks like the true representation of the humerus. So scatter, what is scatter? It's any unwanted exposure to your image receptor. We call that fog. It's usually a result of your Compton interactions. It provides no useful information. Scatter or fog decreases the image contrast. Digital imaging receptors can detect lower levels of radiation intensity and therefore are more sensitive to scatter. So this is what scatter or fog looks like. You can see this is the heart right here, so the cardiac silhouette. This is your aortic knob, aortic notch right there, and it's just not clear and crisp. So that's fog laying on top of your image. Quantum noise is kind of the opposite. So this is where there's not enough photons reaching the image receptor. So visible as brightness or density fluctuations and is photon dependent. So too few X-ray photons result in increased quantum noise. Yes, that's my dog playing with her squeaky toy. Sorry. More visible in digital imaging. So digital imaging is very sensitive to quantum noise. So it has to have enough photons reaching the image receptor, or else you're going to have this snow-like appearance. So this is normal. You can see there's a little line there. I don't like that line. Looks like a fracture line. And then you can see here all the little dots where there wasn't enough photons reaching the image receptor. Image artifact is anything unwanted on the radiograph. It can be a multitude of things. In this one, very clearly, it's a necklace. So you have to remove all image artifacts so that you can see the anatomical tissues. Limitations of film screen imaging. So it's limited dynamic range. The cost of film and the need for chemical processing is a huge downfall. The processing time takes a while for us to process any film. We can't post-process or adjust the image of film. And there's limited contrast resolution, whereas digital imaging, we have really good contrast resolution. And it cannot be stored electronically, and there's huge film archives that we used to have to go dig films out of. These huge rooms full of just tons of jackets. So that is the Chapter 3, Image Formation and Radiographic Quality. It goes hand in hand with the PowerPoint that I posted already. So this should help break it down a little bit more.